first. I don't know. I think I have allergies. I don't think I'm sick. I'm trying to video. Is this videoing? Yep. Okay.
Hi, Nick.
Hi, Nick. Okay, so, but first we're going to start with bond energies, and most of this will be really familiar, so I'm going to do like 2 examples, and then we're good. We'll take a break, we'll do problem set, we'll do bond energy problem set, we'll go back into it and do molecular orbital theory, and then you guys are starting multiple choice. What I can do is tomorrow is like solely after quiz, and then you have a quiz on the Socrative quiz I didn't give you with atomic structure. I can push molecular orbital theory to tomorrow, but I'd rather not. So let's see how far we get today. Coolio?
Coolio.
Okay. So fill in the blanks for me. The more electron rich, rich. They're on those electrons. The more electron rich the bond is, the blank the bond energy. What are your thoughts here?
The longer, stronger.
Energy is related to weak and strong.
Strong.
Stronger the bond energy, and the blank the bond length. Shorter. So, and a good example of a strong and short bond would be a triple bond. Okay, so that's just a qualitative and kind of quantitative way to describe this. And now we need to draw these. We need to place them in order of longest to shortest in O bonds, not no bonds. Okay, so let's go ahead and everybody draw these. It's going to take you a little bit to get through all those. Okay, resonance structures and all. Draw them so that you will be able to do this again on your test. Actually, I'll just draw this with you. Can we just draw these together?
Yeah.
Okay. Okay, this thing, what's your general procedure for doing your Lewis structures? No, first thing, count valence electrons. So 2 plus 5 plus 6 plus 1. I do this still, okay? I've done this for years, like decades, and I still count my valence electrons. You will get things wrong if you do not count your valence electrons, because you will not know total electrons for, like, if there's lone pairs or not. Okay, so what is that? 12, 14 electrons? Is that right? That is still not right. 5 plus 6 is 11, 12, 13, 14. I don't know why I wrote 12 here. 2, 4, 6, 8, 10, 12, 14. Oh, no, that's 14. Okay. Okay, so we have to choose a central atom. Nitrogen or oxygen is probably going to be our central. But commonly, if we have nitrogen and oxygen, I'm asking for the NO bond. They have to be connected. Have to. And then I've got, it kind of shows you in order. I've got N attached to 2 H's. Okay? And I've got an N attached to an O, and then I have an H attached to the O. It tries to show you in order so that you don't get messed up. I feel like I'm missing an H. I think I made a typo. Is it low? 2, 4, 6, 8, 10, 12, 14. There we go. Yeah, okay, there we go. So here's the NO bond. Obviously, it's a single bond, right? Okay, next one. N2O. So 5 times 2 plus 6, 16 electrons to work with. How do you guys want it to go? NO, NON. What are you going to do? Non? Okay, let's see here. I'm just going to go down because I need space. Okay, so what do you want to do after that? Huh? How many bonds? Both double bonds? Oxygen does not like to share electrons, people. It is very electronegative. It's like, gimme, gimme, gimme. Is there a way to let oxygen have more to itself than to share? NO, okay? So that's going to be your kind of trial and error. You'll actually probably go through that and try to get formal charges and stuff, and then you'll realize that, hey, maybe there's a different arrangement. So NO is actually the better arrangement here. And then we've got nitrogen commonly forms triple bonds, okay? It actually enjoys sharing 3, likes to have sometimes 3 bonds, like true covalent bonds, because it likes to fill up its valence shell. So a lot of times you'll see nitrogen like that. I think triple, dot, dot, 1, 2, 3, 1, 2, 3, 2, 4, 6, 8, 10, 12, 14, 16, 16. There we go. This one's obviously triple bond, so it's going to be the shortest or the longest? Oh, I'm sorry, NO bond. Sorry, I'm looking ahead to my number 5. is a single bond, but our single bond here, we could have, what was I going to tell you guys? Oh, we could have, let's see, 2, 5, see how down here our formal charges are around nitrogen here is a +1 formal charge, the middle nitrogen is a +1, and then this one is a -1 formal charge. You could have drawn a double bond here, but the nitrogen have, oh no, the nitrogen have octet, then you'd have double like on each side here. So what I'm thinking is maybe double bond, if you've done double bond to make sure your formal charges are better, but we're okay with that as is. So let's leave that alone for a minute. Let's keep going. You can actually narrow this down from longest to, we're doing longest to shortest as we go through the rest of these. Okay, leaving that there for a second. So then we have 5 plus 6 minus 1, so total of 10 electrons. Okay, so N to O, 10 electrons would be, yeah, where does the plus come from? I know we have to do bracket and plus, but where is this +1 charge coming from? Oxygen's formal charge. So oxygen's got 1, 2, 3, 4, 5. So that's got it's lacking one of its valence counts. So it should have 6 electrons. So it has a +1. So its overall formal charge is +1. Okay, that's how that comes there. So this is definitely a triple bond. No choice about it. It's definitely a triple bond. It's definitely a single bond. Okay, NO2. So 5 plus 6 times 2 plus 1. So 12, 18. No. Yeah, 12, 18, 19? 12, oh, 17, 18, sorry. Yeah, okay. So you guys tell me, what do you want to do? Who's in the middle? And so with 2 bonds, O and O. Do I want double bond both ways?
No, just one.
Okay. So keep that there, then lone pair, 2, 4, 6, 8, 10, 12, 14, 16, 18. All right, where's the -1 charge coming out? The O that's double bonded has surrounding it 6 assigned to it. That 6 fulfills its octet. It's valence. Yeah, this one has got 2, 4, 6, 8. 2, 4, 6, 7. That 7th electron makes this formal charge a -1, which gives overall the structure a -1 charge as it should have because it's that polyatomic. Okay, but I equally could have done what? Yeah. Oh, oopsies. Nitrogen. Have done the double bond on the other side due to the resonance of this. So, all right, I'm going to put the bracket of the resonances. Okay, here's the bracket holding the resonances together. So they're actually an average between these. So the average between this is actually a what bond? A 1.5 bond, because this double bond here and this double bond here could have been on either side. So you take that bond and you split it between the 2 locations in which it can exist. So that's a 1.5 bond. That's a 1.5 bond. Stronger or weaker? No, let's go longer. Longer or shorter than that single bond over here? Shorter, because it's almost a double bond. It's almost the strength and length of a double bond, but it's halfway between it. Okay, so now NO3. 1 minus, is that what it said? NO3, 1 minus? Yeah, okay. So 5 plus 3 times 6 is 18, that's 23, 24 electrons, including this negative charge. So we have, this one's pretty obvious. I think we've actually drawn something similar to this before. Double bond on one of these. Maybe this works out. 3, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22. Octet on everybody. In this case, nitrogen cannot exceed octet, so you have to give it 1 double bond, because the double bond is going to allow for this oxygen over here to have a formal charge of what? 0, okay. Nitrogen has a +1 formal charge. Yeah, and both these oxygens have a -1 each. So -1 + 1, -1 overall. That cannot exceed octet, though. You cannot make 2 double bonds on the nitrogen to try to get these oxygens to not have a -1 formal charge. So each of these have a -1. This is a +1, so they overall account to or summate to -1. But this double bond could have equally been in any other given location. I'm going to quickly draw these. Sorry if my dots look awkward. Or this O and double bond O, O. Okay, now overall, what is the length of the NO bond? 1.33. Okay, because we took the bond that was delocalized, we put it in 3 different locations, so we broke it up into 3 spots. But essentially, is this bond closer to double bond or closer to single bond in strength and length? Single bond. Okay, so in order of longest to shortest bond, who's the longest bond? So here's a list. I'm just going to actually put numbers on. Who's the longest? Who's the first one listed? The single bond. So this is the longest bond because it's a single bond. Who's the shortest bond? So this is number 5. This is the 5th one in the group here. So because there's 5 different 1, 2, 3, 4, 5 different things we're looking at. So who's number 2? The 1.5 one? Oh, it's just not quite. So tell me, who's number 2 in our sequence from longest to shortest? Say it loud and proud. Because that's not. This right here is a. So I'm gonna draw this in here. What was it? NO, N2O. That was. Yeah. Okay. So. Our sex. Okay. N triple bonded to N and O. 1, 2, 1, 2, 1, 2, 2, 4, 6, 8, 10, 12, 14, 16. I think we said 16 electrons on that, right?
Yeah.
Okay. And then if you draw it this way, 2, 4, 6, 8, 10, 12, 14, 16. 2, 4, 6, 8, 10, 12, 14, 16. Yeah. And is there you could go, you technically could go the other way with the triple bond oxygen, but it's just not very preferred. So what I'm saying is these 2 bonds, this triple bond and this single bond could technically be a double and a double. So the average between that's kind of a double bond. It doesn't seem as if it should be, but essentially what you're thinking about is this bond right here between the N and the O can be delocalized and put over there, which is essentially what I kind of just did. I took away the double or this extra lone pair and put it on the other one. So this right here averages out as an average of a double bond. Okay, yeah.
But if oxygen is more electronegative, wouldn't it keep going first?
It would, but resonance says we can do this. We can, I'm not going to say it's going to exactly look like, but that's what resonance says we can do. We're going to talk about that a little bit more today with molecular orbital theory. Okay, so the next longest is, thank you, 1.33, because that's like 1 and a little bit shorter than a single bond. This one, the 1.5 bond, is a little bit shorter than this one. This double-ish bond is shorter than that one, and then the triple bond is the shortest of them all. Okay, you will have to do some comparisons, and you will have to do some visualizations of your resonance structures. Okay, I've already talked about covalent bond a lot. So let's just do a quick review of bond energies again, and we'll do like one example together. All right, so if I'm telling you that the energy involved in this first reaction, methane, me breaking down methane's bonds, why is it a positive number? You what? When you break bonds? Is it endothermic or exothermic? Endo. When you break bonds, you require energy to karate chop it, right? You are putting energy into breaking those bonds. So what's the bond energy of one CH bond? Or what would you do? Say it louder.
The delta H divided by 4.
Thank you, because there's 4 bonds in methane that were broken, and each of them are giving off approximately the same average bond energy. So take that divided by 4. So this single bond has a bond association energy of that divided by 4 is 413 kilojoules per mole of CH bonds. That's what that unit has been. We've always said kilojoules per mole, but moles of what? It's moles of those bonds. So 6.222 times 10 to the 23rd CH bonds. Okay. So if I wanted you to figure out the bond energy of a CCl bond from this information, tell me your thought process. Notice that this is a formation. So you're taking this plus this plus this to form these bonds. Why is this negative? Because when you're forming bonds, energy is, because bonding is an energy lowering process, right? You become more stable when you do your octet stuff, so that's why it's releasing energy. So if I wanted you to figure out the bond energy of CCl, how would you do it? No? Come on, be serious with me.
You would subtract, or you would do 413 times 3.
Because what?
Because there's 3 CH bonds.
Because there's 3 CH bonds that are used that are forming this compound right here. So that is 1239 kilojoules, okay?
And then add that to the negative 1578.
Okay, so this is the energy that's being put into breaking CH bonds. Okay, so I'm going to add it here like you said, but then you got to tell me how the charges work out. 1239 kilojoules. So what's remaining is negative 339 kilojoules, which is the CCl bond energy. CCl bond energy. Okay, so that negative version, though, is talking about the energy to do what to the CCl bond? To form it, because it's releasing it, right? So, but all bond dissociation energies, they're always published in a book or on paper or whatever as positive, because the definition of bond dissociation energy is the energy used to dissociate a bond, to break a bond, to crunch off a bond. So they're always published as endothermic values, okay? So the true bond dissociation energy of it is positive 339 kilojoules per mole of CCl bonds. Okie dokie? Okay, so that's just a quick review. And everything that we publish and everything that we have in books, they're all averages, because it's hard to determine the exact bond energy of something, because it depends on what other substituents are around it, what kind of environment it's in, if it's energetic, etc. So we always publish things that are average. I think we're good. We know the energy released, energy of reactant bonds minus bonds formed, which is product bonds. So tell me how you would do this. How would you find the enthalpy of formation? What does enthalpy of formation scream to you in terms of symbols? Delta H, F. Right, delta H, F. Let's go standard conditions. So that's a little standard conditions up there. It's a little not symbol. All right, so what am I trying to find really? Delta H of reaction is essentially what I'm trying to find. I should know delta H of what? Okay, I can do products minus reactants, or I can do, if I have given, oh, you guys have this in your packet. I give you a bond dissociation energy chart. Pull out your packet for me. I don't know if you have this example, but I know you have the bond dissociation chart. So I know most of the time we want to do products minus reactants, but that's only if you're given the heat of formation of each of these products and each of these reactants. But if I give you a table of bond dissociation energies, did you find that table?
Yeah.
Okay. If I give you a bond dissociation energy chart, you can't do products minus reactants. You have to do what minus what? Yeah, they're actually reactants, which are bonds broken minus delta H of products, which is bonds formed. Okay, so that's the difference with your bonds when you know your bonds, because bonds broken is always a positive value, and bonds formed is always a negative value, which is why we have this negative region or signal sign between the two. So bonds broken would be, you have to draw these out to see the pictures and see the images. Okay, so H bonded to H plus F bonded to F yields, what's wrong with this equation? Okay, so I need 2 HF bonds. Okay, so I just did that. I counted my valence electrons. I put it on here. This one's easy to draw. So the delta H reaction would be, what's the value that I'm looking for first?
H and H.
HH bond. You guys have that for me? 436 kilojoules per mole. Okay. 436 is for the HH bond. Okay, so that's one of the reactants plus 155 kilojoules per mole. For the other one, that's a plus, I'm sorry. Minus
2 times 565.
2 times 565. Okay. Kilojoules per mole for the 2F2 or 2FH bonds. Okay, so that's 590 minus 1130 is equal to negative 540 kilojoules for your per mole for the formation of 2HF bonds molecules. All right, so it's exothermic, and that makes sense because what do you tell me? Bonding is a
Energy reducing.
process. Good job, because it's exothermic. You can see that here. You can always verify a lot of your stuff with logic. Okay, there's another chart. I think that's all I want to do on this. All right, so do I want to do this? Okay, so go ahead. You see the little chart right above that? You have your bond energy concept. I have the ones I want you to do. Start with number 1, and I'll tell you about the ones I want you to do. Because I don't think they need to do all of them. Down. Very cold. Bless you, my child. Sorry, you feel poopy.
I suggest you all go home and get your sleep.
Bless you. Here, let me do the quiet now. Okay, because for the Vesper theory, you said it helps with geometry. The hybridization orbitals help explain why things have same bond energy and same length, because all of the orbitals turn into a new blended morphed shape that allows for us to understand a bit more information about the energy of the molecule. But the molecular orbital theory helps explain why resonance structures exist, why such things are that are called bond orders exist, which we've been saying, like, things like triple bonds and double bonds. Eventually, we're going to call things like that bond order of 1, 2, and 3, and it most of the way does correlate with the bond, single bond, double bond, and triple bond. Most of the way that follows that path. But then we'll have like 1.5 bond orders. You're like, what is that? So that's related to what we kind of did with the resonance structures in our previous example with NO and N2O2 and stuff like that. And then lastly, why some things form diatomics while other things do not form diatomics. That's the last and final piece of our puzzle. And, scientists like to develop these theories to explain every anomaly to the trend. And so we have these theories that cover 90 or 80% of what we see. And we have a couple of other theories that explain the last bits that don't follow the general rules of the first 2 theories or first 3 theories. So that's why, as we discover more things, we have to keep coming up with more explanations to the evidences that we find. So it's going to help us see the existence of diatomic ions or diatomic structures and why some things form diatomically while others do not. Okay, I'll give you guys another second there. So this is valuable in explaining why benzene has a delocalized structure of electrons. Did I do that right? There we go. While it actually doesn't exist as either one of those, it exists as some average where they overlay on top of each other. So each of these bonds, what are they worth? 1 bond, 2 bonds, what? 1.5 bonds. So we're going to see this come into play again too. Okay, so the only things I don't really want you to write any of this stuff down unless you want to, but I just want to explain a little bit more. So previously with hybridization, we said, okay, 4 atomic orbitals come together, they make 4 molecular orbitals. 4 hybridized orbitals, right? This is the same thing. So like for hybridization, we took, S plus a P plus a P. We took 3 orbitals, what kind of hybridized orbitals did we make? S plus P plus P made sp2. How many of sp2 orbitals were we able to make? 3. Because if you take 3 atomic orbitals, s, p, p, you're going to make 3 new orbitals. They just look different. They're hybridized. There's 3 sp2 hybridized orbitals. That extra one, that was that empty or unhybridized p orbital, it was able to interact via double bonding, in that case. So you're still making the same number of orbitals. You're not wiping out orbitals. You're just changing the way they look and their energies and stuff like that. So same story here. You take 2 atomic orbitals, like maybe S and P, and you pull them together, you make 2 molecular orbitals. They're orbitals that surround the entire molecule, and they're really weird shaped, okay? I cannot draw them. The shape, and I have some pictures of them. But the first orbital that forms, that contains electrons, is called the bonding orbital. And another one that forms is called the anti-bonding orbital. So it's against bonding, doesn't want to bond. This one does bond. This one's a little, more college level than anything else we've done this year, okay? So it's okay to not, be the Einstein of this. I want you to get the lingo, and I want you to be able to draw some of these things that we're going to see in a second. So the 2 bonding orbitals, there's a bonding orbital and an anti-bonding orbital. They occur in series with each other. So here's what it looks like. I'll go back up to the top in a second. The bonding orbital is lower in energy because bonding is an energy lowering process. The anti-bonding orbital is really energetic and stressed out and high energy, so it's listed higher in the energy diagram. Okay, so these energy diagrams are used to show the molecular orbitals, because in this case, this is hydrogen and hydrogen. This is like saying hydrogen A and hydrogen B, or hydrogen atom number 1 and number 2. They can come together to form H2. They can, but are they stable enough to fully exist for a long period of time? Well, yeah, we know that because hydrogen naturally exists, abundantly in the atmosphere. So this is the 1s1 electron. This is the 1s1 electron of hydrogen, of each of them. They both contribute that 1 electron to the 1s, not the molecular orbital one, this is the 1s orbital. But when you put them together in a molecule, both of these electrons are going to fill the molecular orbitals, which one is much lower in energy, which is the bonding orbital, one is much higher in energy, which is the anti-bonding orbital. So these 2 electrons come together, and they're going to fill up from Aufbau's principle, lowest to highest. They're going to fill up right here first, but there's no more electrons, right? So this is simple. The 2 electrons exist in the molecular orbital, the bonding orbital, that we call sigma 1s, which is what we call it, because it's a sigma bond, and it's made up from the first 2 electrons in the s atomic orbital. Okay, so that's what these diagrams look like. And here with here are what the 2 orbital types look like. This one is called the bonding orbital because it's showing the overlap. This one's called the anti-bonding orbital because there's like a repulsion between overlap there. So anti-bonding does not bond. Okay, so that's what those look like. And that's what I was saying here. Lowest energy orbitals get filled first. Of course, maximum 2 electrons because that's Pauli exclusion principle rule. And then we fill up past that of successive energies. Okay, so let's do, here. This is what I want you to be able to do. You need to write down this highlighted part right here. What you're going to be able to do eventually is to draw or read molecular orbital diagrams. And actually, you know what? I think I printed this in your packet. If you want to write it again, you can. But I think I printed this slide for your packet. After hybridization. Yeah. Okay, I just didn't do the paramagnetic one down there. Okay, so this is in your packet, but you can write it. So you're going to be able to read or draw the molecular orbitals and calculate bond order. And bond order is simply half, so 1/2 times electrons in bonding orbital minus electrons in anti-bonding orbital. So you have to be able to draw the structure and look at the structure first. We'll do 4 examples or so. So the bond order is valuable in determining if something will exist in nature. It will be stable enough to exist in nature. So if when you do your calculation, the bond order is greater than 0, it's stable enough to exist in nature, and it will naturally occur. If it's less than 0 or equal to 0, it's not stable, definitely if it's less than 0, it's probably never going to exist in nature. If it's 0, it's very unlikely to exist in nature, because there's some things that are bond 0, bond order of 0, and they do barely exist in nature. And also with the orbital diagrams, you'll be able to see if all the electrons are paired. If all of them are paired, what did I say about magnetism? Diamagnetic or paramagnetic? Because they don't, right? They just don't. They don't have any kind of attraction to the magnetic field. And paramagnetic is going to have attractive forces with the magnetic field because there's things that are unpaired. Because they're polar, okay? So we're only going to do that for the homonuclear diatomics, which somebody mentioned that when I asked about reading, guys. It was one of you, Grace or Gabby. So that's what we're doing, diatomic species right now. Okay, oh, let's go back and do the bond order for that example I just had. So bond order for this H2 example, half times electrons in bonding, bonding orbitals minus anti-bonding orbitals. So how many are in the bonding orbitals? 2 minus 0, because there's none up here, and the anti-bonding orbital, so that bond order is what? 1. Generally, the bond order relates to the type of bond, single bond in this case. All right. So, and then the bond order is also going to indicate the energy. If you have a higher bond order, like a 3, generally that means you have a higher bond energy. Higher bond energy, of course, means shorter bond length. So all of this right here is kind of like a massive summary of connecting the dots between all the things that we talked about with bonding this year. I'm going straight to an example. Okay, that's review. I'm going to skip this for a second. Oh, did I just print this for you? I don't know. It doesn't matter. Is there any... Did I print it? No, okay, I'm going to skip this for a second. Okay, so this is the example we just did. Okay, this is on your page I just printed for you. On this one, I actually have the labels of what they call these molecular orbitals. So these are not, the ones on the left and right are the atomic orbitals, and they're showing how each hydrogen number 1 and hydrogen number 2, they have a 1s, 1 electron configuration and a 1 electron configuration. So in this orbital, they each carry 1 electron, not hybridized, not molecular yet, just plain old atomic orbitals. And so these 2 electrons are going to get fed to the lowest energy orbital called the sigma 1s orbital. You can see this one up here is called the sigma 1s star. Star is not good. You don't want to be a star. Okay, stars are anti-bonding. So the sigma star is representing extremely unstable, I'm going to say just unstable and energetic. You don't want to be star. Star means you're unstable, you're anti-bonding. All right, so then you say bond order we just said was 1/2 of 2 minus 0, which is 1. There's bond order for that one. Let's do the next one. Helium. Does diatomic helium exist? Let us see. I've never heard of it. Have you guys heard of it? Diatomic helium? Me neither. Let's see. Okay, so helium is 1s2. Yeah? Each of them are 1s2. So they have 2 electrons in their atomic orbitals. Those atomic orbitals are the 1s, right? They're the 1s orbitals. So where do these 4 electrons get fed? 2 down low, 2 up top. Okay, so there's 2 in the sigma 1s, and there's 2 in the sigma 1s star. Okay, so bond order for this. 1/2, 2 minus 2, so that's 0, right? So that's unstable, that's very unlikely to be found in nature. So we're proving it now. Like, we already knew that. We'd never heard of He2, but it's not forming in nature. These are the homodiatomics that we're talking about. All right, lithium. Now, lithium's got 2 shells. It's got the valent shell, and it's got the inner shell, the 1s. So lithium is 1s2, 2s1. So we've got 3 electrons to be working with, one of which is valence. So I'm going to show you the bottom one first, because this is an energy diagram. Energy is going up right here. And the lowest one down here are 1s and 1s. Am I okay? You guys okay? Okay. These 1s are full. 1s's are both full from each of the lithium atoms. So they're going to be filling up the sigma 1s orbital, and then the sigma 1s star orbital. And then this is the 2s orbital, and we've got we have one electron here and one electron here. This sigma 2s and 2s star need to be filled up now. But these first two 2s electrons are going to fill the sigma 2s and not the sigma 2s star, not the antibonding. So then how do you want to do bond order? What'd you say, 1/2 what? Why 4? Right, this one and this one are the bonding orbitals, so there's 4 minus the 2 that are in the anti-bonding. So 4 minus 2 is 2, divided by that is 1. So technically lithium diatomic can exist. We just don't deal with diatomic metals too much, but it can exist. Okay, last one for now. Boron, did I do boron? Did I do beryllium? Did I just... Oh, you know what? Hold on. I think I just skipped. It's down here. There it is. Beryllium. So let's go faster this time. Here's 1s2, 2s2. This is 1s. This is 1s. 2, 2. So the molecular orbitals, sigma 1s and sigma 1s star gets filled. And then this is 2s and this is 2s on each atomic orbital. And they have 2 electrons, so they get filled. So bond order, 1/2 of 4 minus 4, so that is a 0. So beryllium diatomic will not exist in nature. Nope, ain't gonna happen. So stability of this is nothing. Not stable, not gonna happen. Alright, so you see how this is different than any other theory we've talked about. It's got some different value to it. I'm not saying it's easy, but it's different value. Okay, so this is the last one we're going to do for now. I printed this one for you? Okay. Boron, because now we are dealing with p electrons, and p electrons occur in a kind of a sporadic direction. So I'm going to kind of walk through this one for you first. So boron, starting low, boron is 1s2, 2s2, 2p, 1. Okay. It's 1s down here. Sorry, 1s and 1s, or sorry, sigma 1s, sigma 1s star. It's full all the way because it's got 2 electrons in each boron atom, 1s electrons, so they get filled. And that's not the valence shell. Okay, that's the very inner core electrons, which are difficult to remove. So I just put a division here to show you that. And then we're going to go do the p electrons. So we got to go through 2s before we get to 2p. So let's go ahead and do 2s. Now we know they are also they have 2 electrons in each of the p 2s orbitals. So sigma 2s and sigma 2s star are both going to be filled up. And then I have ordered this in the way that these p orbitals are listed. I've ordered it for you. You do not have to memorize the stacking of this. I will give you a template so you can fill it out. So this is called pi. I just don't have a symbol for pi. This is pi 2p sigma 2p. It does not go sigma to pi. It goes pi and then sigma. Don't ask me. And then this is pi 2p star, and then that's it actually. Okay, so what are we doing? Boron. Boron's got 1 electron in the 2p orbitals. So it's got 1 electron here, 1 electron here, so they have to go down to the lowest, filling in one at a time. Not, these are 2 orbitals right here, so you can't fill them both up before you fill up one at a time. Okay, so how many are in the bonding orbitals? 1, 2, 3, 4, 5, 6. Because those are all the lowest ones, so 1/2, 6 minus 2, no, 4? 4. So 6 minus 4 is 2. Oh, there you go. Bond order of 1 for boron. So boron can exist in nature. It would have a single bond. Yeah. So because the sigma bond has already been approached by us to doing the S, this one right here, the S So you know, like in hybridization where we did sigma bond and then each additional multiple bond was a pi bond. I mean, was it, yeah, anything past a single bond was a pi bond, right? What this is saying to us, and I can show it to you from bond order first, that's telling us it's probably a single bond between those. So you'll notice that I don't fill up well, no, I do fill it up. It's not full though. I was going to say it worked out that way, but it doesn't. It's not full, so it's not going to have a full pi bond overlapping, and that's hybridization anyway, so I can't directly relate those two, but that's how I would think of it. It's because if it doesn't have a double bond, then it's not going to have a full set inside of one of these pi's indicated. Pi in this case, so pi in hybridization means double or triple bond. Sigma means single bond, right? So sigma does kind of mean single bond here, but more than anything, the sigma is just referring to the shape of just more of a circular appearance, and the pi bond is referring to more of a p orbital appearance. That's more of what this is related to in this case. Yeah.
How would this look different if we did like diatomic nitrogen? Like, how do you fill any further?
So I have this summary right here. This is gonna, because instead of us drawing out every single one, I just went ahead and put this on your guys' paper. So you've got, let's see, we just did boron, so look at carbon. Carbon's got 2 extra, each carbon atom has 1 added electron, so combined the carbon diatomic has 2 extra electrons. So we did 2s, this is just the valence shell here, okay? This is valence electrons only in this energy diagram. So the sigma 2s is filled, the sigma 2s star is filled, and then each of the electrons and the pi 2p orbitals are filled, or each of the orbitals are filled. So then that would yield a bond order, I think I've got everything right here, yeah. A bond order of 6 minus 2 in this case. 6 minus 2 is 4 divided by 2 is 2, yeah. 6 minus 2 is 2. 6 minus 2 is 4 divided by 2 for bond order is 2. So this one would actually most likely yield, carbon would most likely yield a double bond between it. Triple bond you can see occurs with nitrogen because we have, after, here's our S block down here, they're similar across the board here. But as you get 2 more electrons you're adding, they're going into the upper sigma 2p, which is still not antibonding. Antibonding's way up here, okay? They're going to be filling it in successive energies. And so that's going to yield 8 minus 2, so divided by 2 is triple bond, 3. The only thing that's more also valuable here, we haven't talked about yet, is the magnetism one. Oxygen over there is paramagnetic because of the unpaired electrons. And then I think that's it for, also what we just did, boron, diatomic boron, was paramagnetic due to the unpaired electrons. Okay, so this is a nice summary page of some of those, but like I said, I'll give you a template like I just gave you. You just need to fill them in. Okay, so that's all I'm going to do for bonding orbitals for now. All right, we have 30 minutes left.